Dear students, last class we have completed thermal equilibrium, then definition of temperature and zeroth law, heat, work and internal energy, and also we have completed the first law of thermodynamics. तार गोटे आज से फर्स्ट लॉ गोटे प्रॉब्लम करबा. Let us see. Let me show you the problem. This is the first law and this is the problem. Look at this. Estimate the increase in the internal energy of 1 gram of boiling water getting converted to vapor at the same temperature by supplying heat from outside. So here you see 1 gram of boiling water getting converted to vapor at the same temperature. You can say, I have told you earlier that internal energy of a system clearly depends upon the temperature. That means no change of temperature means no change in internal energy. But that is true only when the substance is in a particular state, either in the state of solid or in the state of liquid or in the state of vapor or gas. But when substance changes its state from solid to liquid or from liquid to vapor, that change of state takes place without any rise of temperature. Remember, when a substance changes its state from solid state to liquid state by supplying external heat, temperature does not change. The temperature which remains constant during the change of state or change of phase is called melting point from solid to liquid and vice versa. Similarly, when a substance changes its state from liquid state to solid state, again temperature remains constant, heat is absorbed by the system to convert the entire liquid to vapor, and that temperature is called as boiling point. So here is a case of classic case where 1 gram of boiling water getting converted to vapor at the same temperature, means at 100 degree centigrade. Of course, the boiling point and melting point depends upon the external pressure. So at 1 atmospheric pressure, the boiling point of water is 100 degree centigrade. कौन हमको दिया है, देखो सुविधा पाई हमको कौन दिया है जी, the volume of the vapor is given to us. So when 1 gram of water converted to vapor at the same temperature at 100 degree centigrade under 1 atmospheric pressure, the volume it occupies is 1671 cubic centimeter. The second one which is given, the latent heat of vaporization दिया है 2256 joules per gram. That the water absorbs 2256 joules of heat per gram in order to convert from liquid state to vapor state. Then pressure of 1 atmosphere pressure is equal to in SI unit 1.013 into 10 to the 5 Pascal. So एतिकी हमको दिया है बर्तमान हमें बाहर करिवा जे estimate the increase in internal energy. ये तुम कहि पार the temperature remains constant, how the internal energy can rise? Internal energy rises because here the change of phase takes place. A change of phase takes place, temperature will remain constant, but the system will absorb the energy from outside, and that energy gets stored inside the system in form of its internal energy. Let us estimate how much is that internal energy. We shall use the first law of thermodynamics to find out the rise in internal energy. Let us see. So for that, let me take the help of blackboard, a green board. Green board रे बाहर करिया केते होची 1671 2256 मन रखिए. Let us remember these two things. Let me use a blackboard. So कौन दिया है देखा, the mass of water is given mass of water is given as 1 gram. Then what are the other things given? 1 gram of water getting converted to the vapor. Vapor ra volume दिया है. देखिए how much volume the 1 gram of mass will occupy. So volume, this is given. So volume of the water. आगे वॉल्यूम टा बाहर करिया, वॉल्यूम ऑफ वाटर केते हो, मास दिया है, वॉल्यूम केन बाहर हो, मने प्रकार डेंसिटी. Density is equal to mass per unit volume. So volume, so we shall find out the volume from density. So volume of water is equal to density by mass. Density is equal to mass by volume. So volume is equal to density by mass. Sorry, mass by density. उल्टा लिख दिए. So volume of water is equal to mass by density. So how much it is? Mass by density, that is equal to, mass is given 1 gram, and what is the density of water? As you will know, 1 gram per cubic centimeter. This is the volume, so that is equal to 1 cm cube. So this is the volume of the water. Then what happens? So volume, then water will convert it to vapor. So the new volume is हमको केते न्यू वॉल्यूम दिया है, देखि दियो एठी हमको न्यू वॉल्यूम दिया है केते 1671 1671. This is the new volume. So change in volume, delta V is equal to 1671 minus 1, so that is equal to 1670 cubic centimeter. This is the change in volume. एतिकी volume change होउछ. आउ तापर कोन हमकु दिया है, लेट सी व्हाट आर द अदर थिंग्स गिवन टू अस. हमकु latent heat दिया है. Latent heat means the amount of heat supplied to that system to convert it from liquid state to vapor state. So that means the heat supplied to the 1 gram of water kete na latent heat. So the heat required to change the state is equal to mass of the substance into latent heat. Mass of the substance into m into L. Q is equal to m into L. So let us see how much it is. The mass is 1 gram And how much is latent heat is given to us? Let us see how much is the latent heat. 2256 2256 2256 joule per gram. This is the heat required. So gram cancelled. So it is 2256 joule is the heat given to 1 gram of water. So this is the heat given to the 1 gram of water. So you can take it as delta Q. This is delta V. So from the delta V you can find out work done, because when the expands, work is done on the surrounding. So how to find out work done? It is P into delta V. Let us see. So देखो एटी so using first law of thermodynamics, using first law of thermodynamics कौन लिखिए? Delta Q is equal to delta U plus P delta V. So that implies rise in internal delta U is equal to delta Q minus P delta V. This much. So delta Q is how much? Just button call it delta Q. Let us see how much delta Q लिखा है जी 2256 जूल. So 2256 जूल है delta Q 2256 joule. This is the delta Q minus P delta V. P हो जाएगा 1 atmospheric pressure. कितना दिया है देखो? P रे मूल्य दिया है जी 1.013 10 to the 5 1.013. This P है 1.013 into 10 to the power, wait a minute, so it again 10 to the 5 10 to the 5 Pascal. ये है तुम्हारा P. Delta V is 1670 cubic centimeter. So 1670 cm3. एटी दिया है. So now that is equal to 2256 joule minus, देखो पास्कल इज न्यूटन पर मीटर स्क्वायर. पास्कल तुम्हारा प्रेशर न्यूटन पर मीटर स्क्वायर. So we can convert this PA is nothing but Newton per meter square. Okay, and this centimeter cube, you can see this is nothing but 10 to the power minus 6 meter cube. देखो ये ला Newton per meter square, 10 to the minus 6 meter cube. So when you multiply them, meter square cancel. So Newton meter will remain. ऊपर कौन है वो? Newton meter, and Newton meter is joule. So Newton meter is nothing but joule. So this is joule 10 to the minus 6 10 to the 5. So it will be 10 to the minus 1, then it is joule. So how much it is? Minus, you can see here 1.013 into ये 5 है, that is minus 6. So minus 1 means 167 will become 167. So into 167 joule. This much. So this is the case. That is equal to by such upon minus, this is around suppose 168, suppose nearly equal to, suppose it is 168 or 169. So that is equal to 6 ରୁ 8 ଗଲେ 8, 14 ରୁ 6 ଗଲେ 8, 0, 2. So see 2088 joule of energy delta A. So rise in, this is the increase in internal energy. This is the internal energy of 1 gram of water. So you see, when 1 gram of water is converted to vapor, just vapor, you see how much, this much is the rise in its internal energy. So this much of heat it absorbs to get converted from liquid state to vapor state, and this is the application of first law of thermodynamics. So next, there are many applications of thermodynamics. Let us go to them. Let us see. So after, let me go to another case. There is a problem gala. ବର୍ତ୍ତମାନ ଦେଖିବା ଆଉ ଗୋଟେ application ଦେଖିବା. So the second application is specific heats of gas. ଆମେ ଆଗରୁ ପଢିଛନ୍ତି kinetic theory ରେ, ଏଠି ଆଉ ଥରେ first law ପକେଇ ଦେଖିବା the specific heat of gas ବିଷୟରେ ଟିକେ ଆଲୋଚନା ଆମେ କରିବା. So first we shall discuss about, we have already read in the heat chapter, the heat capacity. So what is heat capacity? Heat capacity of a system is nothing but how much heat a system absorbs for unit rise of its temperature. गोटे system को तमे heat देले तार temperature rise करिवो. So heat required for unit rise of temperature is called its heat capacity. So I have defined you, heat energy required for unit rise of temperature is called heat capacity. आमे से heat capacity आसीबा specific heat विषय में discussion करिवा. Let us have some discussion and then derivation. आमे discuss करिवा, then we shall go for derivation. Let us go to another page. And what is heat capacity? As you know, suppose let delta Q amount of heat is supplied to a system or substance, whatever you can say, either you call a system or a substance. The delta Q amount of heat is supplied to a system in order to raise its temperature, in order to raise its temperature from T to T plus delta T. एतिके में देले ताहले केते राइज कर टेम्परेचर डेल्टा टी. So for delta T rise of temperature, heat absorbed by the system is delta Q. So how much heat absorbed per unit temperature rise? Delta Q by delta T. So this is how we define the heat capacity. अतः heat capacity of the substance heat capacity of the substance, हमें जाको लिखो S बोली, capital S. So heat capacity of the substance is delta Q by delta T. What is delta T? Delta T is the rise of temperature. T thila, T plus delta T hela. So this was the initial temperature, this was the final temperature. So final minus initial will give you the rise of temperature, and that is delta T. So this is the heat capacity of the substance. Okay. So its unit is joule per Kelvin. The unit is Joule per Kelvin is the unit. This is the SI unit of heat capacity. Now you see, heat required to raise the temperature, okay? But is it constant for that substance always? No. If the substance is small amount, then small amount of heat will be required to raise the temperature through a particular degree centigrade or degree Kelvin. If the mass of the substance is more, then in order to have same degree rise of temperature, you require more heat to be supplied. Therefore, the heat capacity very much depends upon the mass of the substance. If mass is more, it requires more heat for a 1 degree rise of temperature. Therefore, since heat capacity depends upon the mass, let us now go for defining another physical quantity which will be independent of mass. How can I do it? Very simple. If this is the heat capacity for a certain mass of the substance, then how much is the heat requirement for unit mass of the substance, and that will become a physical quantity independent of mass. So let us define that. In order to make it independent of mass, so heat capacity, so let small m be the mass of the substance. Mass of the substance. অতএব heat capacity for unit mass will be S by M. This will be S by M. S by M. So this heat capacity per unit mass, this is a quantity which is independent of mass and also temperature. So this new quantity is called as, it is called specific heat. This new quantity is called as specific heat, and its symbol is, we use the symbol C. So specific heat is equal to S by M, that is equal to 1 by M delta Q by delta T. So this is how we define the specific heat of a substance. So now let me write that down. So C is equal to 1 over M delta Q by delta T. I'm at aguru padichhan. During time of kinetic theory of gas, we have also read it, where C is called the specific heat. Then, is it applicable to every system or every state of matter? Yes, solid, liquid and gas. But in case of gas, we replace this M, mass, in terms of number of molecules. That is, another unit is there, mole. So mole has a better understanding when the system is in, or when the substance is in gaseous state. In that case, mole is the better one. The through mole, we can find out mass very easily. So this formula we use for a specific heat of a substance when the substance is in either in solid state or in liquid state. So this is used either in solid state or in the liquid state. But when it comes to the state of gas, we use a different technique, that is called, we replace mass by number of moles of gas molecules. So for a gaseous state, the mass is suitably replaced by N. What is N? N is the number of moles of gas particles, number of moles of gas particles. So therefore, the specific heat of gas is defined as 1 by N into delta Q by delta T. This is the definition of specific heat of gas. So here, unlike solid state and liquid state, the specific heat of gas is not always same for a given gas. Even gas is fixed, but the specific heat or heat requirement for unit rise of temperature for unit mole of the substance is not always same. It depends upon two factors or external factors, like if you are supplying heat from outside and allow the gas to expand, simultaneous rise of temperature and also gas expands freely, you have no control over its expansion, then you see how much heat it requires for rise of temperature. Second case is you do not allow the gas to expand. If you do not allow the gas to expand, you will see less amount of heat will rise or raise the same degree of temperature of the system. तार अर्थ तुम्हें गोटे गैस टेम्परेचर बढ़ी पार केमती बाहर हिट देकी बढ़ेब तुम्हें हिट दियो हिट दे संगे संगे कौन कर गैस टाक फ्री छाड़देव आ कि कंट्रोल कर देन जो हिट देल से गैस एक्सपांशन टेम्परेचर बढ़िया संगे संगे एक्सपांशन हम किंतु आउ गोटे केस रे जब एक्सपांशन टाक बंद करदेव डोंट अलाउ द गैस टू एक्सपांड देन यू विल सी लेस अमाउंट ऑफ हीट विल बी रिक्वायर्ड फॉर गिवन राइज ऑफ टेम्परेचर. Therefore, the value of specific heat depends upon whether you allow the gas to expand freely or you do not allow the gas to expand. So requirement of heat will be different in those two cases. So let me write down those two cases. So first case is the case number 1, means allow the gas to expand against a constant pressure and case number 2 is this. Case number 2 is do not allow the gas to expand by increasing the pressure. So do not allow the gas to expand. The two methods, either the system has no piston or no method of or facility of expansion, or if there is a facility of expansion, stop the expansion by applying more pressure on the piston. So do not allow the gas to expand. Either by applying more pressure or by removing the piston facility. और by removing the piston जो गतिशील piston दिया जहाँ जो गैस एक्सपांड कर पूरा उठे दिया गोटे कांथ देकी बंद कर दिया. Stop, there is no scope of any expansion. So these are two ways you allow or you make the gas to absorb heat for rise of temperature. So what you see here, in one case the gas is not allowed to expand. Not allowed to expand means what? not allowed to expand means volume is kept constant. When volume is kept, that means volume is kept constant in this case. The first case is free expansion, allow the gas to expand against a constant pressure. Pressure बढ़ेगा नहीं जहाँ पर gas टा freely expand करेगा. So here pressure is remains constant. So गोटे केस रे pressure constant रहेला, आ गोटे केस रे volume constant रहेला. Therefore the heat requirement will be different in these two cases. In first case, more heat will be required for a given rise of temperature than the second case, because second case केवल volume बढ़ती, no expansion is there. So therefore, depending on the two cases, we define two specific heat of a gas. कौन लिखिए? गोटे होची specific heat at constant pressure. This is called specific heat at constant pressure. Then another one is CV, specific heat at constant volume. So how do we define it? So you see here, so CV is equal to 1 by N delta Q by delta T. Here V is constant. We write it like this. Cp is equal to 1 by N delta Q by delta T, V constant, and Cp is again 1 by N delta Q by delta T. P is constant. It is P constant, right? So these are the two specific heats of gas, Cp and Cv. And now let us use our law of thermodynamics to find out how much is the Cp and how much is the Cv. Let us try to find out by using law of thermodynamics. So liquidity use kore law ta mon rakhile. So let me show it again. So from the first law, my first law कौन जानते हैं? The first law says delta Q is equal to delta U plus P delta V. This much we know from the first law. Now let us try to find out Cv first. So Cv, how much is Cv? Cv is 1 by N delta Q by delta T, V constant. So now we shall put the value of delta Q like this. So V constant means what? V constant means, so V constant means delta V is 0. V constant means change in volume is 0. So in case of delta Q, let us put this value. So Cv is equal to 1 by N, let us see, delta U plus P delta V by delta T. V constant. And V constant means delta V 0. So this goes at 0. So how much remain? Delta U by delta T. U does not depend upon the volume, it only depends upon temperature. So therefore, it is equal to 1 by N delta U by delta T. देखो एठी मु आउ कोनोसी लेखु नाही कोन कांस्टेंट वॉल्यूम लिखिल नाही काहे लिखिल नाही ना U essentially does not depend upon the volume of the gas. So Cv now equal to 1 by N del u by del t एति आम एठू जानले cb एति बर्तमान देखिबा cp केते let us see how much will be cp cb एति हला और cp बाहर करिया so cp is equal to 1 by n delta q by delta t p constant. This is cp, so we put the value of delta q there, so that is equal to 1 by n, then it is delta u plus p delta v divided by delta t. This is p constant. So now you can write down two things. It is 1 by n delta u by delta t. So u does not depend upon the volume, also the pressure here. So delta u remains like this plus 1 by n, it is p delta v by delta t. P delta v by delta t. So how much it is? It is 1 by n. देखो the first term, look at the first term. 1 by n delta u by delta t. देखो it is nothing but cp. So that is equal to cv plus 1 by n p delta v by delta t. So this is cp. This much is cp. So let me find out here. I will divide it कर दो देखो ये. So cp is equal to cv plus 1 by n p delta v by delta t. Let us take suppose 1 mole of gas. मानकर मैं 1 mole of gas नहीं, और simply from ideal gas equation हम use करिए from ideal gas equation we have PV is equal to nRT. PV is equal to nRT. So if you change the volume, temperature will change provided P is constant. So when volume changes at a constant pressure, when volume changes at a constant pressure, what happens? Let us see what happens. Because this is the case of constant pressure case. Pressure remains constant. So when volume changes at a constant pressure, this equation becomes, this equation so this equation becomes P delta V. P का V change ला, एपटे क्या change है वो? It is N R T will change. So when volume changes, temperature will also change. So P delta V is equal to NR dt. So in case of P delta V, you can put here NR dt. So Cp is, now look at that expression. So Cp is equal to Cv plus 1 by n P delta V jar NR dt, n R delta T by delta T. So n cancels, delta T पड़ेगा, तो रहला कितना Cv plus R. So Cp is equal to Cv plus R. That means Cp minus Cv is equal to R. So this means Cp minus Cv is equal to R. This is Mayer's formula, you can call it. In chemistry, you can see it is Mayer's formula. The Cp minus Cv, the difference of Cp minus Cv is R. And remember, the specific heat of gas which we define in terms of moles, not in terms of mass, that is called molar specific heat. Specific heat of gas as it defined in terms of number of moles, it is called as molar specific heat. So whatever I have told you, it is written there, you can see here. Now see, the specific heat is the heat energy required for unit mass of a substance for unit rise of temperature is called specific heat. This remember, this specific heat, it is for which state? And this is for solid and liquid state. This is for solid and liquid state. And you see, next one is then other one is molar specific heat. So heat energy required for mole of a gas for unit rise of its temperature is called as molar specific heat. Then comes, so these are two applications of first law of thermodynamics. तापर आसिला हमर after thermodynamics, we shall now go for the next topic. Again, we shall apply the first law to this process. It is called thermodynamic process. So what do we mean by thermodynamic process? As I have told you earlier, a thermodynamic system is expressed or described by some parameters which are called as the state variables. What are they? I have told you in the first class: the volume, the pressure, the temperature, the amount of substance, means mass or number of moles, and finally the internal energy. So these are the 5 variables which I have already told you. They define a given state of thermodynamic system. Due to external or internal effects, whether we try to disturb externally to a system or some internal thing happens within the system, like when a petrol gas exploded inside the heat engines, like your petrol engine, now you have got petroleum gas, petrol in a vapor form, and when sparking plug sparks, suddenly a large amount of heat is generated and the volume of the gas increases. So that is internally happens, of course, by external agency. So when the system undergoes a change of state, means because of any change in its state variable, it is this process when system goes from one state to another, from one equilibrium state to another equilibrium state. That process is called thermodynamic process. Remember, the state variables will have a fixed value at the initial state and a fixed value at the final state. In between, the values may change. Pressure may change, volume may change, temperature may change, internal energy may change. Of course, quantity of matter does not change, because we are not allowing in the higher secondary class that we shall see the quantity of matter almost remains constant. We shall take a closed system where we allow the pressure, volume, temperature, internal energy to change without affecting any leakage of the gas or any gas coming inside to the system. Mass of the gas remains constant and pressure, volume, temperature and internal energy will change. So a system can move from one equilibrium state to another equilibrium state, and the process of going from one equilibrium state to another equilibrium state is called thermodynamic process. And I have discussed these state variables. See, what are the state variables? State variables are volume, internal energy, mass, pressure and temperature. Then we define, just for sake of definition you can say, remember it, we just define two type of state variables. They are extensive state variables and intensive state variables. So what is extensive, what is intensive, let me explain you here on the board itself. So what is extensive and what is intensive state variables? Let me show you here. First one is extensive. So what do we mean by extensive state variables? Extensive means, suppose you have a system, let us take a system here. आम system नेले चारिपटू बंद, चारिपट you have got insulating walls, and you have a certain amount of gas in it. अभी तो सारा gas अच्छी, and its pressure is P, volume is V, temperature is T. So यार pressure है P, volume V, temperature T, and internal energy is कितने ना U. U is the internal energy. Now let us see. Let me divide it at the half. मुठी को आधा कर देंगे. मुठी को आधा कर देंगे. एपटा फाड़े कर दे, सेपटा फाड़े कर दे. Just by introducing a wall in between. Half कर देली. Now you see, तुम देखिबो एपटे जो प्रेशर थिला सेपटे सेही प्रेशर रहइबो. टेम्परेचर एपटे जहाँ थिला सेपटे टेम्परेचर सेया रहइबो. Same रहइबो. Pressure, temperature will remain same. Because why? Pressure is force per unit area. So आधा आइला, area भी आधा आइला, piston area. And what about T and V and U? Total volume थिला V. So now its volume is V by 2. Here the volume is how much? V by 2. And what's about internal energy? Internal energy is how much? Number of molecules into half kBT. You have already read it. So U is also becomes half V by 2, U by 2. And also if its mass is, suppose number of moles is N, so here number of moles is N by 2 and number of moles is N by 2. You see. So V by 2, U by 2 and N by 2. Look at this. It is mass like it. So what you see here, the pressure and temperature on both the sides are same. How many parts you make, the pressure, temperature will remain same, because pressure, temperature are the average value of the system. Average value of the system. So if you make it half, no change. But number of moles or mass of the system will be halved, volume is halved, and consequently the internal energy is also halved, because internal energy very much related to number of gas molecules. So these three quantities, the mass, volume and internal energy, gets halved when the volume is halved. But pressure and temperature in both the halves will remain same. So they are called as intensive variables, and these three are called as extensive variables. Okay. So now this is the state variables. The given state of a thermodynamic system is described by a set of values of P, V, T and U. When these values remain constant, we say it is in equilibrium state. Due to some external factors or internal explosions, the system may undergo from one given state to another given state, accompanied by changes in these state variables. So when system goes from one equilibrium state to another equilibrium state, the process is called as thermodynamic process, which I'll discuss exhaustively in the next class. Thank you for watching this video. Go and try to read your books and get ready for next week's class. Thank you. अब ये इसको मारिए.